Good. So now you can hear me even better. So let's see. I usually start with, okay, what's going on here? This I have to get rid of. Okay, now I'm on. All right, sorry for a little bit of distraction. I always start with my usual motto. I mean, I do know very little, and as you will see by the end of this talk, and frankly, by the end of this conference, we just learn how much we don't know. Now, the subject of my talk today is the superconductivity, 2D superconductivity or surface superconductivity that we discovered recently in one of canonical topological materials of second generation canonical topological materials, antimony 2 tellurium 3, at remarkably high temperatures. And we still don't understand why this temperature is so high. But the question, of course, that everybody is asking, myself included, is, okay, so we see 2D superconductivity or surface superconductivity in a topological material. Is it topological? And as you've seen from various talks today, and particularly from the beautiful talk of Dr. Iwaya, it's not so simple because a lot of time, material parameters, and other things basically prevent you to see the usual signatures of topological superconductivity. So what are those? Well, there is, of course, zero bias anomaly. You look for Majoranas. If you have topological Josephson junctions, you look for 4 pi the periodicity of the Josephson junctions. And so the question is, of course, what are the real signatures that we can search for? Can I move this a little bit? And today I will show you that actually, as always by serendipity, that's my way of doing things, we actually found remarkable low energy modes in the superconducting system that are seem to be surface modes and perhaps are related to something that is topological. And I will not be stronger than that because this still is somewhat unusual, and certainly there is no theory of that, so a lot of speculation, and I would invite you to, as experts on Josephson junctions, especially in the systems with unusual order parameters, to suggest or to come to me with some ideas that may explain that. So before I go on, this is my group. The person hemming down here is the main driver on the new data that I'm going to show today. And this is our new lab. We moved into this new shiny building. My lab is right in the basement of this building. And we have a fantastic nanocenter there, so we can make all these gated devices now, which we do, of course, and other things as well. And I will be a mess if I will not acknowledge my collaborators outside of City College. This is Vadim, who keeps me honest. Abe, who does STM for us. Kyunghwa Park, who does DFT calculations for us, and some of the data of Nader. Zaki on ARPAS I will show as well today. So let me just, before I go on, give you a little synopsis. So the system we're looking at is antimony 2 tellurium 3. And I would like to just make sure there is no copper doping, there is no iron there, and there's no arsenic there, okay? So nothing that can give you some sort of superconductivity by doping. And the key thing that I've talked about before is that we do modify bridge, we grow our own materials. So we do modify Bridgman growth. And it turns out, again, we've discovered what very tiny change in growth conditions gave us very strong correlations, while structure, both crystal structure and Dirac structure, was preserved. What we found is the presence of Dirac puddles, which is not new. People have seen Dirac puddles before in STM, and we find that as well. And we find from STM patchy landscape of superconducting gaps where some of the gaps were of the order of 25 millielectron volts, very high, Okay, and there is quite wide distribution of this of these gaps. We also found that the carrier density in the superconducting state on the surface actually is lowered. Remember, if you've seen the data with copper doping of bismuth, selenium, or or other materials, once the system is doped to become superconducting, you actually increase electron density or charge density. Now, this guy is actually a Hall conductor. Okay, and what we found that just by tiny change in growth conditions, the Fermi level moves into nearly into the gap, the bulk gap. The carrier density really goes down by orders of magnitude, and mobility becomes very high. So we really have very high mobility system. And I will show you that this is actually two-component system where the superconductivity is carried by a system of Dirac superconductors, Dirac puddles, that are hosted by high mobility 2D electron gas metal. Okay, and this metal is what I'm going to discuss today, which I haven't done in the previous things. I also will show you some new ARPAS data showing that the surface states remain, and of course the question is why high TC. But then this is sort of a question that I will not be answering, and I try to avoid, because in the high TC community, still people ask this question without much success, I would say. Now, the question, of course, the big thing is, of course, what is the role of strong spin orbit? And spin orbit is very strong in the systems, okay? And there's another thing that I will not discuss today, but something that we've published a couple of years ago. There are these flopping Dirac spins if your chemical potential is exactly a Dirac point, and that might play a role in superconductivity as well. But what I will talk about today is actually the Josephson network that is formed in this two-component system, and I will show you the new data on the resonances in this that became very interestingly, and perhaps indicate that there are pi junctions, frustrated pi junctions, and perhaps even related to unconventional order parameter. So let me just remind you of what this antimony tellurium 2. This is actually the original calculation by Su-Chen Zhang. You have the nice Dirac cone at the gamma point. As you see, the valence band is actually quite complicated, and calculation, of course, do not take into account about charge defects in the bulk material, but actually, the Fermi level in all bulk materials of bulk crystals of antimony tellurium are p-types, so the Fermi level is actually usually very deep into valence band, and the carrier densities are pretty high. Which I will show you actually that in our super sample, the Fermi level is just below the Dirac point, and it cuts a little sliver of the valence band, which is our 2DEG, and that I will show you today. So the first thing we saw is just this, okay? So this is just resistive transition at very unremarkable, well, I mean, it's respectable temperature of 10 Kelvin, but nothing to write your mother about. And at first we thought, it's similar to what people have seen before. However, the puzzle started later, because when we looked at the carrier density, which is I mentioned here, this is on this side, this is the pressure, synthesis pressure. We found that there is a very non-monotonic behavior with the synthesis pressure where carrier density actually goes down by 2 orders of magnitude. The carrier density goes, 3 orders of magnitude. It goes from 10 to the 20 to 10 to the 17 per centimeter cubes for bulk. At the same time, in this region, the diamagnetic signal just shoots up tremendously. Okay, so this is measured by AC, and the other thing that we get from transport, that only in this region of parameters we have huge mobility. In normal standard high topological materials, the mobilities are the order of, well, maximum 3,000. We have seen 10,000. We actually had bismuth tellurium crystals in the bulk which had 10,000, but this is really very large, and outside this region, the mobility is actually here of less than 1,000. So suddenly we have access to this extremely mobile electron gas, and the field dependence is also very peculiar. At first, you look at this field dependence, and this is just a resistive critical field or a limiting field. And so TC is around 9. This is not remarkably high, but what you see here is that anisotropy here is very low. And this is surprising at first. It was surprising at first. Because the structural anisotropy is huge. The C-axis parameter is 30, and AB plane is less than 4. So we expected huge anisotropy. Of course, it wasn't. But the key here, again, and I want to emphasize it in all of the systems, and in this one in particular, that the G factor, okay, is huge. Okay, we actually, and so it can be between 30 and 60. Okay. Here is the Esr measurement by one of our collaborators, Wolosh, that shows around 30 and anisotropy about 1.4, which is exactly what you would expect if this is paramagnetically emitting field. And in fact, if you do sort of really sort of back of the envelope estimate of what this would be and calculate TC from here, you would expect that TC, because of this large G factor, would not be 10, but around 60. So at first we were really puzzled by this, and we weren't sure how to interpret this. What we came to is, and something that was confirmed in STM measurements, is that we have actually a distribution of gaps. Okay, and so this is the STM data from Abe, and I'm not gonna go through that in detail. You can read it in the paper, but the key is that we can see gaps where if you just do the simple BCS estimate, you'll see that TC should be indeed anywhere, locally between 0 and 70 Kelvin. Okay, at least in these measurements, local gaps are as large as 25 milli-electron volts. Now the key was that those these gaps were actually very sparsely in these regions of many scans of 25 by 25 nanometers were really very sparse, about 100 to 200 nanometers apart, which is actually a pretty big job for STM to do. But that convinced us that we have some sort of a puddle system, and mesoscopic superconducting puddle system. And furthermore, if we looked at magnetic response, or what I would call mesoscopic Meissner effect, this is actually DC squid measurement, the big change, and I mean, this is not 1/4 pi, it's clearly much less here because the system is sparse. It's also around 60 Kelvin, and if we look at the AC susceptibility, we can beautifully fit it by the usual omega squared dependence, which is the what one would expect from a two-component system, generally for two-fluid system, normal per super system. And in fact, this is expected for resistively shunted Josephson junctions. And if you look at the data here for AC susceptibility and look at this frequency-independent parameter here, it actually shows, first of all, it shows that unlike the critical field before, it shows huge orbital anisotropy, and again, some sort of mesoscopic Meissner transition around 60 Kelvin, consistent with what we see in DC. So somehow we have a puddle system, and actually we see a very small resistive signature which disappears at high fields in resistivity as well. But this is very hard to track because it's a very tiny blip on the whole landscape. So this is very hard to track. So what I argued before was that now you see we have a system where the carrier density actually drops down by over 2 orders of magnitude in the regime of superconductivity, and that there's huge carrier mobility. And I'm not showing you this. We also see the beats in the Haas-van-Alphen, which are 2D, which are typical of semiconductor beats in d electron gas. We see huge diamagnetic anisotropy and local super gaps. So basically, I'm trying to argue that what we have in this system, it's kind of a mess. Okay, it's puddle Dirac system plus metallic matrix, which is 2DAG. And so we have some sort of a Josephson network with two energy scales, one around 10 Kelvin and around 50, 60 Kelvin. And the question is, of course, what is this system is and whether indeed there is some indication of topological superconductivity here. Now, first thing, of course, was to check whether we still have Dirac states. This is actually published data by another group. Remember, this is a standard ARPAS, and since these systems are p-type, you only can see the states up to the Fermi level, right? So you see this. This is part of this surface state here, which continues over there, and so this was published data on this material. This is our super sample, and it looks the same. But the question now was, okay, so what about all the stuff that is subsurface? Okay, whether that can give us some sort of a clue as to topological or proximal superconductivity, if you will, in this surface system. And yes, indeed, this is Nader's data, ARPA's data, where he actually probed subsurface states by changing the energy of electrons in ARPAS. And two things he found. One is that the subsurface states have threefold symmetry rather than sixfold symmetry of the valence band. This is just a cartoon. The other thing that Nader found is that if you look at energy dispersion, energy momentum dispersion, I'm losing this, I don't know what. My ear is still there? Yes, thank you. Thank you. And the analysis that he had done basically looked at the map of the subsurface states. And one thing that was actually quite remarkable, that the subsurface states were also linear. They kind of look Diracish, but obviously they're not surface states, right? But they're linear, so the mass, I mean, depending where is your chemical Fermi level is, the mass is still, the particle is still very low mass. And if you map it carefully, and there is a lot of variation in the system, obviously. So this is Ky, this is Kx, this is the energy or intensity. And this transparent red or pink plane is where the Fermi level is. What we can get is actually the cross-section, the Fermi cross-section, from which we can estimate the carrier density. And this is our data on the same samples, the Husman-Almas data, where we look at quantum oscillations. And this notation I will explain in a moment. But basically, they give essentially the same Fermi surface cross-section, which corresponds to carrier density of the order, bulk carrier density of the order of 10 to the 17, which corresponds to surface carrier density of about 10 to the 13 centimeter square, which is very low. So our picture was here. And you see, so this is sort of a cartoon of what we have. We have Dirac puddles, and we have this strong spin orbit coupled 2DAG, a high mobility 2DAG. And first, you start screening in the puddles, and that's what we see in susceptibility. And eventually, the same long-lived quasi-particles that contribute to quantum oscillation also mediate Josephson coupling and eventually proximal proximity percolation path that gives us the global TC. So the question we ask is, of course, this is not the only path, and this is a messy system. You have a lot of those Josephson loops, if you will, there. Some weaker, some stronger. And so the question, of course, was to see whether we can think about these loops that are arising everywhere on this surface and to give us some information about the nature of superconductivity, this two-component mesoscopic superconductivity. So I still have time. Good. So this is the first data I'm going to show. Okay. So what we're looking now is we're looking at chi prime AC susceptibility. This is note the frequency range here is in around 7 kilohertz. It's a low frequency, okay? Which, well, to me was surprising at first, but we can discuss that. And think about this very, very messy landscape, okay? With many loops, with things going on. What we see is just 3 features there. That's it, okay? And so, and maybe, yeah, so what I called paramagnetic peak in AC susceptibility, and there are diamagnetic troves, if you will. They go down in the susceptibility. This is magnetic field. This is the sign of the amplitude of the signal. Chi prime. Chi prime. Okay? Sorry. That's what I said. I mean, maybe, okay. So now, this is our paramagnetic limiting field. Nothing below, or very little below. There is some fine structure there, which I mean, I can discuss because I'm not going to show it here. But basically, the whole action comes here. This disperses, like so. And this paramagnetic peak actually sits in a trove of a diamagnetic trove. And they're kind of dancing with each other. I'll show you this in a moment. This is actually quite interesting. And so again, so this is all starts around here. And in fact, there are some interesting features at lower fields, which I cannot discuss here. Now, so these 3 features, this, and off resonance, it's what I showed before. If you look at chi prime now as a function of field, you see, I mean, all this susceptibility behaves just like what we've discussed before until you get to this paramagnetic limiting field, and then it's hugely enhanced on this paramagnetic peak, okay, and depressed on the diamagnetic peak. And so this is actually quite remarkable. Now, this is sort of the same data now. Now, you see its amplitude here of chi prime, so this is chi prime. I just showed it in projection. So you see this diamagnetic trough, paramagnetic peak, and there is another feature, diamagnetic feature that am I 3 minutes? Okay, cool. Now, the interesting thing here is that this paramagnetic peak sits in this diamagnetic trough as well, and it is only seen in zero field cooling. So there is history. Dependence, and there are slips, if you will, that I will not have time to discuss, but they happen, so you have these shifts. So again, this is field, the out-of-plane axis is susceptibility, this is frequency, and there are slips that occur right at the paramagnetic field, only in ZFC. There's nothing that we see in field cooled. Now, so the interesting thing, and 1 more minute. Is that okay? There is a temperature dependence, okay? And at our global coherence temperature, something happens. The zero field, the paramagnetic peak and diamagnetic peak just violently split. And let me just show you how it looks like on a better scale. So now again, this is chi prime. This is temperature, this is frequency. This is where we saw the global coherence achieved, and where this paramagnetic peak basically kicks out of the paramagnetic peak. And at the temperature where we see the mesoscopic Meissner effect, this paramagnetic peak basically bifurcates and levels off and disappears. So the key here is that in these resonances, at high fields, we actually can reproduce these 2 temperature scales related to the original superconductivity. And so the question is what it is. And in fact, you can see here on this plan projection that it's exactly at the same temperature scales. Now, so there is a saturation at high temperatures. There is a highest amplitude at low temperatures. And there is strong frequency dependence with temperature. Now, so what could it be? And this is the last thing I'm going to show. Could it be a paramagnetic Meissner effect? I don't know, those of you who remember those days of paramagnetic Meissner probably who remember that, which was explained by many things, by randomly oriented pi junctions, by flux compression, by giant Bordeaux state. But paramagnetic Meissner cannot be here because paramagnetic Meissner basically has to do with field cooling, okay, or flux or vortices. So it's not that, okay. And so the question is, it still could be prostrated pi junctions, and in fact there is quite a bit of work on D-wave pi junctions where unconventional modes, low energy modes, have been predicted. We don't know that. There is no theory on p-wave superconductivity for this, and so it's possible that those are subgap modes of different Josephson junctions, which would be an alternative signature of Majorana's. So I'll end there, and I'll end where I started.
Thank you very much. Yeah. So unfortunately, there is no time.